Welcome to today's SMPTE Standards Update webcast. This quarter's topic is the Perceptual EOTF for Extended Dynamic Range Imagery. I'm your host, Joel Welch, SMPTE's Director of Education. Welcome, everybody. Hope your days are going well, or your evenings, depending on where you're located. If this is your first time with SMPTE's Standards Updates, it's a series of quarterly one-hour online interactive webcasts. And this is where we take an opportunity to share with you what kinds of work has taken place in SMPTE's development efforts. And we pick a standard, give you an update so that you know what's going on and where things are progressing. Unlike our monthly educational webcasts, which are SMPTE member benefits, the Standards Update webcasts are free for everybody. In addition, sessions are recorded for on-demand viewing convenience. Today's speaker is Scott Miller. Scott is Senior Member of Research Staff for Dolby Laboratories, and he's going to talk to us about EOTF. And Scott, if you click on the slide, you should be able to take control and advance them. So without further delay, the floor is yours.
Great. Thank you, Joel. Thank you, everybody, for joining us today. I'd like to talk for a little while here about EOTFs and extended dynamic range imagery. So we'll jump right in. As Joel said, we can try and take a couple questions along the way. We'll have to try and keep it fairly tight, but there should be time at the end. So thanks, everybody, for joining. So I'm going to start right off the bat discussing what is an EOTF and why is it important enough that we're talking about it today. So for those who don't know, EOTF stands for Electro-Optical Transfer Function. And essentially, in this digital age, it's describing how to turn these digital code words in a video signal into visible light at the display. What I want to stress is for creative imagery, which is what we're talking about mostly in SMPTE, the image on the reference display is actually what defines the signal in the end. An artist is going to make creative decisions on how they want the content to look while they're viewing a reference display. And this can take many forms. It can be the traditional sitting at a grading desk in a post-production suite, or it could be sitting in front of some live camera control units during a live broadcast. But those controls are going to be adjusted, and those are going to be adjusted to present an artistic image on the reference display that the artist is watching. So what that display does is critical to define essentially what the content is. Also, interoperability absolutely depends on consistent image reproduction. That reference display must match any other reference display, otherwise the creative image will be distorted. So the first question is, where is the EOTF in current standards? If we look at things like typical SMPTE 292, SDI standards, 372, or even HDMI, there's no EOTF in these. They're basically interface specifications. They don't say everything about what the RGB and YCBCR values they contain mean. They talk a lot about how to get the bits down pipelines. They talk a lot even about potentially what white point is used or what color primaries are used, but they don't really describe the curve we need to convert those signals back into light at the display device. Going deeper, we can look at things like ITU, Rec 601, 709, even the latest Rec 2020, but again, none of these standards contain any mention of the EOTF. These are all set up as encoding specifications that define the opposite end of the spectrum, the OETF, the Opto-Electrical Transfer Function, which is essentially the camera capture curve. And you might think, well, doesn't that define the EOTF? It would just be the inverse of the OETF, but actually systems don't work that way. The image display function is not the exact inverse of the image capture function. This is primarily due to rendering intent. Basically, the assumption is most scenes are captured in a much brighter environment. The display environment is generally much dimmer. Therefore, some image tweaking has to happen on a systematic level to make the images look correct because of the different reference ambient. So the natural question is, where is our current EOTF defined? Well, it's defined right here. The current gamma nonlinearity is based on CRT physics. It's been pretty much the same from the beginning. And amazingly enough, this was not fully standardized until 2011 when the ITUR came out with BT 1886. Essentially, in a way, we didn't need a standard because CRTs were ubiquitous. That's what was used in all the reference displays, and they all worked pretty much the same. So the CRT essentially was a physical standard, even though there was no documented standard. So with CRTs becoming quickly extinct and being replaced by other display technologies, a strong effort was made to officially document their response curve, because as we said before, it is this EOTF response that truly defines the signal. So it was important to get a real definition on this before the CRTs all went away. So just a quick recap, OETF functions, as are used in Rec 709 and the like, are actually derived from the display EOTF, not the other way around, even though the standards might lead you to believe otherwise. Because essentially the EOTF, as we said, was determined by the CRT physics. That's just the way the devices worked. The OETF was actually created based on, you had to do an inverse EOTF, obviously, and then add the rendering intent in. As we said before, EOTF definition is necessary to view the finished content properly. If you don't have a roadmap for how the display is supposed to operate in this digital age when the gamma nonlinearity is not intrinsically part of the display, you have to define it exactly, otherwise your monitor may not match someone else's. By contrast, the OETF definition is just a rough target. Anybody who's done professional production knows camera curves are adjusted constantly for preference during shooting, and sometimes to match each other. The textbook Rec 709 EOTF is almost never used in practice. It's always got some kind of tweaks, normally certainly a knee at the high end, and many other things are added, again, by personal preference. So why do we need a new EOTF is the next question. Ideally, an EOTF should be defined by the human visual response for best efficiency and functionality. The current gamma function worked well enough for the CRT era, basically because we're talking about perceptual EOTFs here, and gamma is a sort of perceptual EOTF, but only at relatively low luminance levels and relatively small dynamic ranges, which is what we pretty much had in the CRT era, so it worked fairly well. Now, some have suggested we could just stretch or tweak the gamma function a bit to let us squeeze a little bit more brightness and dynamic range now that our display devices can handle it, but we believe next generation systems are going to be much brighter and have much higher dynamic range. And we believe that because we think viewers will demand it. So why do we think that? Well, as we started down this road of higher dynamic range research, that was a main question in the beginning. What would viewers prefer? So to try and answer some of those questions, we at Dolby conducted an extensive extended dynamic range viewer preference study. So to do this, first off, we had to create a very wide range display, so you can see it on the right on this slide. Essentially, it's a 6 kilowatt digital cinema projector projecting its image on a roughly 20-inch monochrome LCD panel. And using our dual modulation technology, we could create a system that had a very wide range capability. It does a P3 color gamut, and it could do roughly a luminance range of 0.004 to 20,000 candelas per square meter, or nits. The experiment was conducted with a 3-picture height viewing distance, and it was done in a dark, a cinema type room environment. We decided to go with the cinema or a dark home theater viewing environment for the most conservative numbers, Obviously, if the display environment gets brighter, you would probably want brighter imagery as well. So, not to go into too much detail, but this is a quick summary of the preference study results, along with some typical displays. So what you can see here is we did essentially 3 different pieces to the preference study. One was in black preference, how dark did people like shadows and dark areas of the screen to get. Another was white preferences. This is for large area objects such as for outdoor scenes, maybe snow or sand. For indoor scenes, it could be a white tablecloth or white pieces of paper, things like that, large area objects. And then a separate study was done for highlight detail, because this is where a lot of the higher brightnesses in extended dynamic range imagery come from. It's not large area pieces, but it's small elements of the scene, little specular reflections on jewelry or water that just give the image some extra pop. You can see the preferences here, and again, we won't go into detail now because of time. But you can see the blacks, the preferences, as you get darker and darker, more and more people are satisfied with the results. And you kind of asymptote up here around where advanced displays are today, 0.01 and lower down to 0.001 perhaps. On the white end of the scale, we kind of come up here. We're in the couple hundred nit area up to maybe 1,000 or more. We found some interesting things there too, and there are different preferences. Once you take the shackles off of the old display technology, you actually start finding different preferences for indoor scenes versus outdoor scenes, as you might expect in real life situations. And then for highlights, things go further yet, and again, it kind of asymptotes up here in the multiple of 10,000 nits area. What we had to do then was decide what area we'd like to target for our extended dynamic range system. You can see where the standard TV falls now, or roughly, we'll call it 0.1 to 100 nits. You can certainly extend that a little bit in either direction, but this is where the bulk of video material lies today. You can see a more advanced display like the Sharp Elite, much darker blacks, and it can go up towards 1,000 nits in peak output. Even more advanced higher dynamic range displays like the Dolby Pulsar, again, go very dark, and we extend the range even higher to around 4,000 nits. We decided to, we took 10,000 nits as a high level for our system, just because that's where things start rolling off in terms of preference, and it was a nice round number. But also, we look at the dark end, and again, things start rolling off somewhere in 0.01, 0.001, but there are some advantages to being able to go even darker yet, and we'll talk a little bit more about that. And these levels come almost for free in defining the system, so we let it go all the way down, essentially to 0.
Scott?
Yes, sir.
We do have a couple of questions from our guest, Scott Wilkinson.
I thought we might.
He asks, what is the resolution of the digital cinema projector in the preference experiments, and why use 3 picture height viewing distance?
Good questions. The resolution of the projector, I believe, was 2K. The reason we went with 3 picture heights is it was we weren't trying to target the cinema necessarily, even though we're using a cinema projector, obviously. 3 picture heights was, it's kind of kicked around as the defined viewing distance for HD TV, and since our system was about the same resolution, we went with that. Obviously, you have different scenarios in UHD or cinema where you'd get closer than that. A lot of home viewing is done farther than that, so 3 picture heights seemed like a good place to start.
Thank you. There are no further questions at this time.
Great. So we'll skip ahead just to put some more details to the data. When we talk about black numbers, reference video today, generally a reference CRT is somewhere between 0.005 and 0.01 nits. Reference cinema is actually a little bit brighter because of limited contrast in the systems now. 0.01 to 0.03. The best consumer devices today can get down towards 0.001, and this is pretty dark. Although it turns out, true black is a very elusive target. If your visual system adapts long enough, you can literally see handfuls of photons in a very dark environment, but that's not very useful for entertainment viewing. What we find is about 0001 candelas per square meter is very dark. Even in a pitch black room, it takes a minute or two to adapt down to that kind of level to tell that it's not true black. And even after that, it's still very dim looking. So, getting down to these levels is useful for what I'll call the big gray rectangle effect. When you go into a dark home cinema or home theater room, and you kind of see that floating gray screen on the wall. That's definitely something we would like to avoid if we could. So going to these dark levels can potentially do that for you if the display is capable. The visual system limit is actually down to around 10 to the minus 5 or 10 to the minus 6, though the color vision cuts off at about 0.003, where the cones shut down. On the other end of the spectrum, reference video today is about 80 to 120 nits. 100 nits is kind of the general go-to number for this thing. Reference cinema is defined as a 48 nit white point as a reference, and the best consumer devices available now can actually go above 1,000 nits, even topping out at around 1,500. We have commercial devices today like the Dolby Pulsar and some others that can do 4,000 or 5,000 nits peak. And 10,000 nits, although it seems like a pretty extreme number from a video or cinema sense, it's actually not too hard to get a real-world look at. It is actually the typical brightness of a fluorescent tube. If you have an open fluorescence fixture nearby, you can basically look at that tube of light, and 10,000 nits is a pretty reasonable number for that. It's bright, but it's certainly not painful to look at, even in an indoor environment. So 10,000 is not as scary a number as it may seem at first. So let's get back to the EOTF. Now that we have a roadmap we've set aside for ourselves, we're going to look at this 0 to 10,000 nit dynamic range and see what it takes to utilize that with a perceptual EOTF. We're going to assume a practical system is going to need to be... Yes, sir. Another question?
Sorry, we have one question that came.
Certainly.
Yes. This comes from our friend Bill. Bill asks, what is the real-world white for cinema at any given moment in any given theater?
That's a moving target as well. Obviously, 48 nits is the reference level. So if you have a perfectly calibrated theater, it should be able to reproduce whites at that level. As we know, typical cinemas don't tend to hit that level. Bulbs age and dim. Certainly 3D systems are more challenged in terms of light levels. I know there have been studies done, and there are many cinema screens, I believe, that are well under half that number, and many 3D screens that are well under a quarter of that number. So others would have more data on that than I would, but there is quite a range out there, just as there's quite a range of typical TV white levels as well.
Great. No further questions at this time.
So we're going to assume a practical system is going to need to be somewhere in the 10 to 12-bit range these days. Current infrastructure is going to limit us there, not only interface pipelines, but a lot of silicon pipelines as well. 12 bits is kind of the extreme that we can do for now. We want to use the human visual system to determine the performance we need, because that's our ideal to start with anyway, and we'll look at that and start fitting some curves. So the next thing I want to introduce is this contrast step curve. This is what we would traditionally call the delta L over L plot. So along the x-axis we have luminance, going from darks increasing in brightness to our 10,000 nit number here. On the y-axis we have the contrast step, the minimum step you can make in a given system. So going from code word 1241 to code word 1242 is a certain increment in in terms of percentage, and that's what we plot on this y-axis here. What we throw on this curve is kind of a visual threshold level. This is taken from an ITUR report, BT2246. This has to do with the UHD-TV standards, which became Rec 2020. There was a lot of discussions in there about visual aspects of the system, and this was one piece of it. This is something they called the Barten ramp, coming from the Barten model for human vision. And this was kind of a consensus threshold at the time for normal imagery in a system like that. So basically, anything above this edge, the theory says we have the potential for being able to see those step edges. So one code word up from another is a potential visual edge. And this could manifest itself if you tried to do a smooth-looking gradient on the screen. You might actually be able to see visible contouring or banding in that image. If you're below the threshold, then in theory step edges are not visible and smooth gradients are possible with your system. So to put some real-world examples on this is OpenEXR, a 16-bit floating point system, and as you can see, the response of this system is well below the Barten threshold, as you'd expect, and any step made in this system should be completely invisible. If we go back to gamma, as defined in Rec 1886 now, essentially what we get is this, and to be able to do a 10,000 nit system with gamma and be below this Barten ramp curve, we essentially need a 15-bit system. As you can see, we're pretty tight to the curve up here on the low end of the scale, and as we get to the high end of the scale, it diverges more and more. This is kind of a well-known response with gamma systems, and essentially what we're doing is we're wasting a lot of bits in the bright regions. We're encoding a lot of extra precision here that we are not going to be able to see. So it's not really giving us any benefit, but it is costing us in terms of code words, which is why we need this large 15-bit precision. Just to put this in context, I wanted to add today's system, which is 100 nit peak, 10-bit gamma. And you can see here why gamma works fairly well today. If you limit it to 100 nits, you don't need as many bits, and it actually becomes a much more reasonable approximation to this Barten human visual response. It's not too far off the curve across the board. It's only when we go to higher dynamic ranges, pushing up into this area of the plot, where gamma starts to fail us, which is what we're talking about today, why gamma is not appropriate for larger dynamic ranges. So we can switch to log encoding instead, and we see here we have kind of the opposite effect. It tracks the Barten curve fairly well at the high end, but it's, again, wasting code words at the low end. We're encoding a lot of levels here, again, that we would not be able to see. It's a little bit more efficient here for the large dynamic range because of this log part at the top. So we only need 13 bits now, but again, not completely ideal. And what we'd really like is something that more approximates this curve itself. So obviously, the natural question is, why don't we go there? Well, so here's the Barten model. Defines a contrast sensitivity function. It's not the most approachable thing in the world, and it would be a little bit difficult to standardize something exactly like this. The other issue is this model does not describe the curve itself. It just describes what the contrast sensitivity of the human visual system is at any given point. So this is only the start to our model, but it is a good starting point, so that's where we go. What we do is we want to create JND steps with this Barten model. So first we take that mathematical model we saw on the previous slide. We choose the parameters conservatively. We picked a 40-degree angular size. Again, as we discussed before, it's a good mid-range value, and it actually turns out to be a pretty conservative number in terms of where the JNDs fall. If you get too large or too small, it tends to be easier on the system. 40 degrees is kind of a sweet spot to make it easy to see artifacts. The other thing we did is vary the spatial frequency at every luminance level. The Barten model predicts that your contrast sensitivity has a different peak frequency at different luminance levels, so we took that into account as well. Once we have all the parameters chosen, we basically select our peak luminance level, in our case 10,000 nits, and then we iteratively calculate the rest of the steps, and we'll talk a little bit about how exactly that's done. Before we do that, this is what I was talking about with tracking the contrast sensitivity peaks. This Barten model actually predicts many curves, and this is a plot of the model at several different luminance levels, going all the way from 001 to 10,000 nits at the top here. You can see a lot of the higher luminance levels kind of compress into almost one curve, and the peak is roughly at the same spot. But as you go much, much lower in luminance, the peak starts to drift downward. You can see the peak goes to lower and lower spatial frequencies. So again, as we build our model curve, we took that into account to be the most conservative curve possible. What we do then, once we know this sensitivity function, which the Barten model spits out for us, then we know the modulation threshold, the minimum modulation you can see given all those parameters, and that's just the inverse of the sensitivity. And then from the definition of modulation, we know the relationship between the two luminance levels under test, and this spells out the relationships here, kind of culminating in this relationship between the upper and lower level. What we do is take those and then put it all together. So for any given, let's say we have a code word that puts out a luminance level of 100 nits. If we're sitting at 100 nits here and we want to know what the very next higher code word or what the next luminance level that we can just barely see above 100 nits, we multiply by this fraction of modulation thresholds. If we want to know what the next lower value we could see is, we do this fraction instead. So to build our curve, we're not necessarily interested in exactly 1 JND, but 1 JND or less. What we do is add this F number, which we'll call the JND fraction, where F is less than 1, and we just multiply the modulation threshold by that, so we can do fractions of a JND step instead of just whole JND steps. So then what we do, start with our 10,000 nit peak level, and we calculate the whole lookup table from 10,000 down. We start with 10,000 in this equation here. We calculate what the next lower level would be given some JND fraction that we pick, and we step down to that level, to the next level, to the next level, until we get all the way down to our bottom code word. Then what we do is look at the bottom code word and see where we ended up. As long as we're close to 0, which is the absolute black level that we want, then we're happy. And what we do is vary this this JND fraction number until both ends of the range are in a good place for us. What we found was for a 12-bit 10,000 nit peak system, an F number of 0.9 creates a good 0 reference point. It's about 10 to the minus 6th, which is about the limit of human vision. So basically about 0.9 JNDs per code step in a 12-bit system gets us to where we want to be.
Scott?
Mm-hmm.
Sasha asked a question. Why can't you combine different functions where appropriate to fit the Barten model? For example, gamma for black and log for midtones, etc.
Absolutely, absolutely. Another good question. I'll back up a couple slides here. Yeah, as you can see, you could almost do something like that. You could use a gamma curve down here, and then you could use a log curve up here, create some kind of piecewise function to create a reasonable EOTF. The main reason we don't want to do that is then you get a slope discontinuity where the two connect, and unfortunately that discontinuity is kind of right in the heart of the range that we care about the most, right in here between 1 and 10 nits, essentially, where a lot of signal values fall, and that can create some unwanted artifacts along the way. So that's why we would, although it can be done, it's not the most desirable thing. But yeah, it is kind of where we're headed. You know, that general shape is what we want. So if we can reproduce that with a smooth, continuous function, we'd be happier, which essentially is what we're trying to do here.
Okay. We have a couple other questions if you have time.
Sure, let's try it.
One question is from Robert. He asks, what is meant by JND?
Oh, I'm sorry. I probably didn't say that along the way. JND stands for just noticeable difference. So it's basically usually a statistically derived number where typically half the population can see the step and half the population cannot. So it's somewhere right around the visual threshold.
Okay, and one more question before we get back to the presentation. It is you're using Michelson contrast definition within Barten's CSF. Shouldn't it be Weber definition instead of Gabor patches, constant patches, to define contrast? Will it be any different?
Yeah, as it turns out, we selected this based on, yeah, as you say, using the Gabor patches is where the Michelson contrast tends to be used. We decided on that. The similarity is very close between the two. As we looked at the numbers, this is kind of the procedure that DICOM used as well back when they defined their system using similar concepts, and we essentially piggybacked on that to create our curve. And the goal in the end was to basically establish something with based on the formulaic approaches, but then test it with real world visual testing and make sure it lined up, and the results of the visual testing lined up very well with the mathematical definitions we had here. So we ended up happy with the result.
Thank you.
So we'll go from here to say this is great. This builds us a nice iteratively constructed lookup table that defines a perceptual quantizer function, but it would be great to have this in one closed functional form. Reason here is it's very helpful for standardization to be able to point to a function rather than a set of functions that lets you build this iterative lookup table. It's also much simpler to document. We can write down one function instead of having large tables that would have to be replicated by different devices. Also, if you have a closed function that's invertible, that's very useful because then you can define closed form functions for both the encoding and the decoding curve. And thankfully, we were able to find good alignment with a modified Naka-Rushton model. This is it's kind of a model from vision science to model cone response of the eye. But a modified version of it actually tracks this iterative LUT pretty well. This little plot here just shows the two plots together. This blue one is the iterative LUT that we were just talking about building, and then the red curve is the model function. So they track very well across the range. And this is what it looks like. The final function is in this form, basically a ratio of some power functions, and it's got a couple of constants defined here on the right. And this is what we call the perceptual quantizer, EOTF, or PQ for short. And laying its response back on our original graph, we can see it accomplishes the goal we were trying to. It mimics this curve very closely, as it should, as they're both derived from the Barten model. And it accomplishes the goal we wanted. We have our gamma-like response at the bottom, we have our log-like response at the top, and we do a smooth, seamless transition between the two, so we should have no issues with discontinuities along the way that could potentially cause visual artifacting in motion video. So one last thing I wanted to cover is the first question we usually get as we talk about these things is, isn't doing a 10,000 nit system overly ambitious? Wouldn't this waste a lot of code words that we won't be using for a while until display technology catches up with our ambitious goal? So the short answer to this is no. The reason why is the logarithmic shape of the PQ curve at the top end. Remember, it looks a lot like a log function there. it gives you substantial gains in brightness without costing large numbers of code words to do it. So basically, we can think of our 10,000 nit range as just headroom for future expansion. The headroom it takes in PQ to go from, let's say, a 5,000 nit peak system to a 10,000 nit peak system is only about 7% of the code space. So we're not taking up large numbers of codes to reserve for that room. And another way to think about it is the midpoint of the code range is actually around 100 nits. So very typical levels today are right in the heart of the range. So as we see with extended dynamic range imagery, the goal here is not to create a vivid mode on steroids, let's say. Most imagery is going to be very similar to levels where it is today. What we're doing is just opening up the artistic palette for bright areas of the image, very bright specular highlights, light sources in the image to have that extra headroom and give it that visual impact that extended dynamic range can give. But a lot of the levels we're used to are the levels that are going to be there in the future as well. And again, this range is constructed such that the heart of the range is serving what we have today and what we'll have in the future. The other point is brighter displays are coming. We already have consumer devices that are 1,000 nits and above, and I expect this time next year we'll see many more. They are on the way. There are technology improvements coming that make it possible with great efficiency, and we want to have room for that in the future. Now, if we were using traditional gamma curves, this kind of headroom would be a much bigger issue. Just to put some plots to that, this is the variation for a PQ style signal. If we go from I did 5 sample systems here ranging from 500 nits all the way to 1,000 nit peak. So if we did our same system but we started with a 500 nit peak instead and then built a PQ table from it, essentially here's our delta L over L curve again, and you can see fairly small differences even going over an extreme range of 500 to 1,000 to 2,000 to 5,000 to 10,000 nit peak signals. It really does not impact the precision of the system all that much. By contrast, if you tried to do that with gamma, all the curves are somewhat elevated to start, as we saw before, but then each increment costs you much more in terms of precision. Another way to look at this is to look at the code word utilization. We'll start with gamma this time. So this is the same type of system, and what I did here is I wanted to divide up the code word space and show how many code words in the range are serving which areas of luminance. This green section here is what I call the most typical object range. So not too far different from what we see on displays today, 1 to 250 nits roughly in brightness. Going below that, we have the shadow detail range. This is what I'm going to call 0.01 to 1 nits, and then I just call the levels below that the ultra black range. Above that, we have the white range, 250 to 1,000 nits. And then highlights being 1K to 5K, and what I call super highlights, 5K to 10K. Things that would generally be very small objects, very small speculars on the screen. If we look at what a 500 nit gamma signal does, it allocates things reasonably well. Most of the, this green range, that's kind of our most important range, is well served. Little bit of room for shadow detail. Maybe we'd want more, but it's got some. We got some good range for the whites as well. Obviously, we're not doing highlights here because it's only a 500 nit system. As we increase the peaks to be able to get those highlights, you can see what happens in a gamma system. Again, gamma is kind of skewed towards the high end. It uses a lot of code words to encode the high-end luminance signals. What starts happening is we allow more and more room for the white range here at the expense of the typical object range and the shadow detail. And that just continues along the way as we go to 2K, as we go to 5K, as we go to 10K. You can see by the time we get up to 10K, we're using well over half of the code words to represent only highlights in the image. Obviously not where we want it to be. We've relegated most of the typical object range to only 20% of the code words, and shadow detail is squeezed down to almost nothing. By contrast, a perceptual space scales much better as you go across these luminance bands. Again, same numbers here for PQ signals, 500 nit peak all the way up to 10,000. And as you can see, as we allow more and more range in the system, we start picking up the highlight ranges here, but at much less of a cost to the normal objects, the white range, and the shadow detail. And you can see, by contrast to the gamma system, the shadow detail area is much larger. So we get what we see in the actual images, much more precision rendition of fine shadow details as well. So just to summarize, before we open it up for questions, we need a standardized EOTF. It's important for interoperability. It's important to define a new system for extended dynamic range. And perceptual quantization is the most efficient way to encode this. We have a large range we need to encode, and traditional gamma curves just aren't sufficient for it anymore. In a perceptual system, each code value corresponds to just under a perceptual step by definition, so we have the least amount of wasted codes possible. And I want to stress a 10,000 nit system actually does make a lot of sense. We've seen that the extra dynamic range is both appreciated and preferred by viewers. We've seen this not only in our visual experiment, but over the last couple of years of working with extended dynamic range imagery, having lots of professional colorists do final grading work on these 4,000 nit displays. The results are stunning, and it's just a no-brainer preference by almost everyone who sees it. It also gives the system headroom for display improvements in the future. Even though we don't have any 10,000 nit displays coming down the pike anytime soon, we may be surprised how quickly they come, given a system in place that can actually deliver them signals that they can use. And again, no more bits are required to do a 10,000 nit system versus a say 1,000 nit system. So it basically doesn't cost us much in terms of precision, and it gives us all that future headroom, and we expect to see it coming soon. And at that, we'll end the formal part of the presentation and just open it up for questions.
Excellent, and we have about 15 minutes for questions, and we do have quite a few very good questions. I'll start with one from Steve. Steve asks, how many people were tested to arrive at the original black and white numbers?
So the original numbers, and I believe there were on the order of 3 or 4 dozen participants in that study.
Okay, and a question from George. How much independent validation has there been of the validity of Barten's model?
Another good question. As you know, there are several human visual models out there. Actually, many of them track reasonably well with each other. We chose Barten just because it's a convenient one. It's been used by a lot of people over the years, and it's proven itself worthy along the way. Barten actually went to great pains in his book where he lays this model out to document how well it fits basically several decades worth of visual experimentation. So we have a pretty good confidence level in the model itself. And like I say, we started with this model just to create a mathematical construct that we thought would be a good starting point, and then went into visual testing with that to just to make sure that we were on the right track. And the visual testing has pretty much backed up the validity of the model all the way.
Okay. Scott asked the question, why does 16-bit OpenEXR look like a sawtooth?
Yeah, another good question. I should go back to that slide. So in a delta L over L plot, this is basically our OpenEXR here. So since it's a floating point system, what you're seeing here is a bunch of linear segments that basically get reset every time the exponent bumps up by a number. So every time that exponent shifts from one number to the next, you'll see this little hitch in the delta L over L. And then the linear section takes over where the exponent is fixed, and the mantissa just counts down, or counts up in this case, and then it resets at the next exponent step.
Okay. Let's see. This question from Alexis. I might reword it a little bit, but let's see. Are there not wasted code words on the low end? Since other EOTFs seem to allocate 4 values at the higher end or higher range, whereas this one seems to have more on the low end versus other EOTFs.
Well, it depends on the EOTFs we're talking about. Certainly compared to gamma, actually, this is a good slide to be on. So yeah, gamma has many more code words at the top end than the PQ does. But in this case, what we're saying is essentially on this plot, those code words don't help us at all because they're well below the visual threshold here. So even though there are many more code words there, they're not doing anything visually for us. So we'd rather utilize those code words elsewhere. If we look at a log system, it's actually the opposite. You know, log system has many more code words on the bottom end of the scale than PQ does. But again, they're code words that don't do us any favors visually. So why waste them?
Okay. Are you up for an audio question?
Sure.
Okay. Let's see. Scott Wilkinson, the floor is yours.
Thank you. My question is, what is the state of acceptance or implementation of PQ as a standard in the professional community and also in the consumer electronics community?
Mm-hmm. Yeah, good question. We're fairly early along on the path here for extended dynamic range, so things are essentially moving through the standards communities now. We've been showing these things to many folks, both on the consumer side and on the professional production side over the last couple of years. The acceptance has actually been very good. I think once people start using these things in practice and see that the visual imagery really does back up the science behind it, they get quite comfortable quite quickly. So yeah, we've had very good response, and as I said, it's we've been at this a couple of years now, doing a lot of professional colorists in Hollywood and around the world have played with some of these systems, and they work quite well.
Okay. D. Adams asked 2 questions. How does the curve compare to ACES proxy? And have you developed an ACES QDT or ODT for this? I think I need glasses.
Yeah, ACES proxy, let's see, let me back up. I'm trying to remember where, and this is where I got out of the, my involvement was less at the tail end of that, so I don't know exactly where ACES proxy ended up in the end. As I recall, it was a more log-like function just because they were after something mathematically very simple. So in those terms, I would guess it relates kind of, well, on the slide we're just looking at here, the PQ curve as it relates to the straight log curve there. There's probably a similarity between that and the ACES proxy. Is there an ODT for this? Yes, there is.
Okay. Bill asks, how does this apply to saturated RGB primaries at max code values?
Okay, so if you did an RGB system at max code values, essentially all of these curves would end up the same. So if whether those codes are PQ or they're log or they're gamma, if they're all at maximum level, then you're at maximum level for the system. These different EOTFs basically just they define the curvature of the system between the minimum and the maximum points.
Okay, and we do have a question. It's asking if you could define ACES proxy and QDF, QDT, ODT.
And
Is it ODT?
ODT, yes, yes.
Thank you.
ACES proxy, and I'm not the best person to do this probably, but my recollection of ACES proxy is it's basically an integer form of the ACES file, which is ACES itself is an OpenEXR encoded system. They wanted a proxy version of it for use in systems that could not handle the 16-bit floating point. So they wanted essentially a 12-bit integer version of the system. So it's kind of ACES proxy is a range-limited integer version of ACES, which I believe is based on a straight log function, if I recall correctly. The ODT is again something in the ACES workflow that's called an output device transform, and that would be a mapping from your ACES file, which contains the original data, how to map that into a display device. So essentially, that's what an EOTF is. I mean, it's a map from digital code words to linear light. So this EOTF is absolutely possible to put into an ODT, and actually we have built, I think, a couple different ODTs based on different ranges of output devices based on PQ.
Thank you. Next question from Mike. Let's see. Were temporal frequency and spatial frequency considered when building the JND curve?
No, we did not take temporal issues into account at all building the JND curve. Generally, these levels are, especially for the Barten model, are spatial only. They are not. There's no temporal component to them. It adds another level of complexity to do anything temporal, and it can go both ways. Some types of banding artifacts are more difficult to see. Some are easier to see as things move. So we decided to kind of forego that level of complication in the mathematical analysis. It's definitely something we test for in practice in the system. Once we were building physical systems, we did a lot of temporally varying test patterns as well, just to verify that the system was robust.
Great. We have about 5 more minutes. Next question from Brad. Is there any work being done to add high dynamic range in HD displays to extend current HD's lifespan, or is HDR only being considered for UHD displays?
It depends who you talk to, I think. I would envision at some point we would see HD displays with extended range capabilities. It only makes sense, I think, to have a range of different technologies available. Right now, I think it's possible to do on both sides, and I think it will be. Like I say, I think it's likely that it will end up in both places, both higher resolution and standard HD resolutions. But again, these things are all moving through standardization now, and whatever the committees decide is what will come first.
And the first part of the next question is, will PQ be standardized? The second part is, if so, would it be necessary to invert it to obtain OETF and revisit encoding in color spaces like BT 2020? Will it be an amendment or a new standard that must be followed?
Again, very good questions. So yes, we are looking at standardizing perceptual quantization functions right now in a couple different bodies out there. So that's all work in progress. I lost the second part of the question now. It
Oh,
was.
sorry. I thought I was muted when I coughed. I didn't mean to.
No, I don't think we were muted. It just went out of my head for a second.
Oh, okay.
We're talking about standardization.
Would it be an amendment?
OETF, right. So yeah, in terms of an amendment versus a new standard, that I'm not sure of. I would expect. Well, I don't even want to speculate on that because it's just one person's opinion. But obviously, there's the bodies will decide how they would like to proceed in terms of amending old standards versus creating new ones. Mm-hmm. And I think either way is potentially workable. In terms of the OETF part of the question, yeah, absolutely. New OETFs would have to be defined for these systems as well, and we're kind of actively investigating that now with some different camera manufacturers and people on the capture and creation side of things. So I think as before, where you have a OETF function that is not the inverse of the EOTF function, we'd have the exact same situation here. The OETF you would want to use in a practical system would not be the exact inverse of the EOTF, but we do have an inverse EOTF function for PQ, and you would take that as a starting point then and add some rendering intent, just as you do in current systems today. So you would create essentially an OETF that has both the inverse EOTF and some rendering built in, and we do have some kind of draft versions of those we're working with today, and again, they are producing just excellent looking results, so more on that to come.
Okay, we have about a minute left and 17 questions to go. So to our guests, I did ask Scott if we ran out of time with questions, if we'd be able to send him those that went unanswered, and would he be able to answer them, and he has graciously agreed. So I think I will ask probably one more question, then close for the day, because Scott does also have an appointment he needs to get to. And let's see. Were these tests done in a completely dark room, and were there any objections by dark adapted viewers to very bright content?
Yeah, that's exactly something we wanted to see. As I said, we wanted to really see how this played out in a dark room. Obviously, if you put these kind of images outside, they wouldn't look like much at all. 10,000 nits outdoors is pretty typical, so that's nothing to worry about at all. But we were very curious what preferences would be in kind of a dark home theater or cinema type environment. So that's why we started there. The room was not completely dark. There was we actually had some green LEDs in the room simulating a cinema exit light scenario. But otherwise, yeah, it was fairly dark. And like I say, we got the plots I showed before, which showed, yeah, there were definite preferences to go to, and I'll talk about white levels in general because that's maybe the more interesting point. People were very willing to go to, let's say, 1,000 nit white level, or even 2,000 nits for outdoor scenes. This is like scenes of a glacier or things like that in the snow. They were very happy with 1,000 or 2,000 nits, even in a very dark room, which was a little surprising at first. But yeah, it's you adapt very quickly, it seems.
Okay, very good. And I'm afraid that's all the time we have for today. We do have a number of other questions, which I will send to you, Scott, shortly after the presentation, or after we close. I do want to thank you, Scott, for putting together the presentation and presenting today. Thank our guests for taking time out of their busy schedules. It is a busy time for everybody, but hope you found value, and take care. Thank you, Scott. Thank you to our guests, and we'll see you next time. Safe travels, everybody.